Okay, now let's talk about the slope of a tangent line to a curve. Is kind of a review, but just to make sure that we are on the same page. A tangent line is when a line touches a curve at the point of tangent C, and in this case, the diagram that I've drawn, the red line is a tangent line, point P is a point of tangent C, and touching the curve at exactly that point. And only one point they can touch. And the footnote to that is that it cannot cross the curve. It can only touch the curve, and that's it. So the slope of tangent line to a curve given by the equation y equal to f of x, that's a function, at the point of A is given by this statement. M represents it as a slope, but is the limit as h approaches 0 of f of a plus h minus f of a over h. And I have included this diagram to look at the geometric representation of that. So we have this f of x curve, which is right here, y equal to f of x. We have this tangent line, the red line is a tangent line, and the point of tangency P, the value of the x value is a, but if we move that to a plus h, that means there's a h value distance between the two x values. Now we will have another point that I can set up, and this is where the limit comes, is that if you choose another point on that curve, let's say point Q, and then you can actually look at the values, the y values, which will end up being f of a plus h minus f of a, because the values of the q, the coordinates of the q are those as well, because we have a plus h, that would be the x value for q, and the y coordinate is f of a plus h. Now this PQ, line segment PQ, is the secant line. And this is how the limit works. Now, as the Q approaches closer and closer to P, if this Q keeps moving towards P, notice that the value of H decreases. That means H becomes closer to 0, and once it hits P, then there will not be any value of H left. And at that point, this is why the limit comes through. So this is where we talk about limit as h approaches 0. When that happens, the secant line becomes the tangent line, and you can see that. So you can see that the slope of this tangent line is given by this statement, the limit statement. So it turns out that the derivative, so the notation that we are using for the slope of a tangent line to a curve, which is this limit statement for the function, is actually the derivative of a function at a, and is given by the same equation, but the notation is f prime. So this little tick on top of the between f and a is called f prime. That's a derivative of function f at point a, and the limit statement is still the same, which is the same as the slope of a tangent line. The only way that works is that if the limit exists, and if that's the case, you have the same value for the slope as you take the limit. Now there is another way of writing this derivative which is simpler, and that is basically, instead of h, you use x and a, and the limit of f of x minus f of a over x minus a, the difference between the two. And that's basically simply what is happening, is that instead of having x plus h here, you're replacing it from x plus h. This would be replaced with x. That means that it's just x value, and of course the between h will end up being a x minus a, right? So this distance now will be x minus a, and once you get that, the vertical value will end up being f of x minus f of a. All right, so simple as that. And this is another statement which is the same as this statement, pretty much the same, but in terms of a simpler form, because it represents the slope of a tangent line. And once you get the slope of a tangent line at any given point, then you can come up with the equation of a tangent line to that curve, and then we can analyze the curve concavity, the behavior of the graph based on that.